Hello students, myself Dr. Divya, Assistant Professor at Department of Chemistry, Institute of Aeronautical Engineering. So in this session, we will understand the calorific value and different types of calorific values like gross calorific value and net calorific value. So here are the topics. Before going to types, we have to understand what is really a calorific value, how is it really defining the fuel's quality, then the types of calorific values. So Dulong's formula for calculating calorific value. So Dulong, a scientist, has proposed a formula for calculating the calorific value. Then octane number. So what is octane number and its use, and C10 number. C10 number and its use. So what is calorific value? So we have been learning fuels and many times we are speaking about calorific value of particular fuel, whether it is a solid, liquid or gaseous fuel. Even the solid, liquid and gaseous fuel, all these types of fuels should possess good calorific value. Good calorific value. So this seems to be very important. Whenever we are saying this sentence, it seems that calorific value is very important when we are using a fuel. So what does it really mean? So the total quantity of heat liberated when a unit mass or volume. Why we are saying mass? In the case of solid, we are saying it as unit mass. Unit mass. And in the case of liquid, it is the volume we are considering. So when a unit mass or volume of a fuel is burnt completely. So whenever we are burning fuel, what happens? There is some heat or the energy coming out of it. So that is nothing but the liberated heat. Whatever is coming from that fuel that is completely burnt is called as calorific value. So this really indicates or identifies the efficiency of that fuel. Efficiency is its importance or its working capacity of that particular fuel. So wood, for example, the solid fuels, example wood has a calorific value of 17 kilojoules per gram. So only for 1 gram of wood, we have 17 kilojoules of energy that is liberating when it is burnt completely. So the amount of heat can be measured by following units. So there are different units that are being used to express this calorific value. So what is that? Calorie, then kilocalorie, then British thermal unit. So in this next, centigrade heat unit. So these are the different types of units used to for expressing calorific value. So if we go in detail, what is a calorie? It is the amount of heat required to rise the temperature of 1 gram of water through 1 degree centigrade. So 1 gram water, when it is rising to 1 degree centigrade, it is nothing but it is evolving heat. Heat is required. So heat is required to rise its temperature. So whenever we are rising the temperature of water of 1 gram to 1 degree centigrade, that is nothing but called as the amount of heat called as the calorie. So that is the basic definition of calorie. So that is a unit that we are expressing. And kilocalories is equal to 1000 calories. So 1000 calories is equal to 1 kilocalorie. 1000 calories is equal to 1 kilocalories. 1000 calories is equal to 1 kilocalories. So it can be defined as the quantity of heat required to rise the temperature of 1 kilogram of water to 1 degree centigrade. 1 degree centigrade. Whenever the heat that is used to rise 1 kilogram of water to 1 degree centigrade, then it is expressed in kilocalories. 1 kilocalories is equal to 1000 calories. Then British thermal unit. So whenever we are saying British, so just remember that 1 pound. 1 pound. So the quantity of heat required to rise the temperature of 1 pound of water from 1 degree through 1 degree Fahrenheit is nothing but British thermal unit. So this is expressed in the Fahrenheit expression of units. So this is the English system units that is used. Whenever we see BTU for fuels like coal, it is nothing but we are using English system unit for expressing this type of fuel. So 1 BTU is equal to 252 calories. So that is nothing but when it is converting to kilocalories, 0.252 kilocalories. So 1 kilocalorie is equal to 3.968 BTU. So that is how we use the conversions to express. So depending on our applications in different countries, we use these expressions of units. So if we see in detail, like SI unit, in SI unit system, for solid and liquid fuels, this is for solid and liquid fuels, we are using and expressing. Why we are using kgs? Because solids are mass. So kilocalories per kg. Why we are using meter, cubic meter? Because it is the volume, that is volume occupied by gas. So that is why we are using it in cubic meter. So in SI system, for solid and liquid, kilocalories per kg or BTU per cubic meter. So in the CGS system, it is calories per gram and calories per cubic centimeter. In MKS system, it is kilocalories per kg and it is kilocalories per cubic meter. So this is how we express for solid, liquid and gaseous fuel. Whenever we are using CNG gas, so or any other LPG gas, then these are the units to be used. And if we are using coal or petrol, this is the units we use for expressing. Then BTU units, BTU per LB and BTU for square feet. So this is how we use the different units. And CHU is nothing but the centigrade unit. So CHU per LB and BTU per cubic feet. So this is how the conversion takes place, and the major conversions between different types of units of calorific value we can see like this, like 1 kilocalorie per gram or kg is equal to 1.799 BTU per LB. That is equal to again 1 calorie per gram. So this is how we keep on converting depending on the expression of particular fuel. Then if we go into details, like the calorific value is expressed in two ways. So with fuels containing hydrogen, two types of calorific values are distinguished: higher or gross calorific value, or GCV, or HCV. So this is the higher or gross calorific value, lower or net calorific value, or net calorific value. So these are the two types that are used. So what is the gross calorific value? Gross is the total, that is heat available, that is heat liberated from a fuel. Total heat that is liberated from fuel, whereas net has some deductions. For example, in money we call net pay and gross pay. So net has got some deductions. So loss. In this case, it is loss of heat in different forms. So the actual heat that is being application for, that is used for the application, is nothing but NCV, or net calorific value. That is how we differentiate these two calorific values, and they are used widely in calculating and distinguishing different fuels and their capacities. So higher calorific value, or the gross calorific value, can be defined as the total amount of heat liberated when a unit mass of fuel is burnt completely. So it is burnt completely, and the product that is generated during this combustion are cooled to room temperature. So we have a fuel here. We are burning it So we are giving heat. So there is evolution of heat. So heat is liberated. So this heat, whenever it is burnt completely, only ash is leaving left over. So again it is room temperature. When it is at room temperature, the heat that is generated is nothing but gross calorific value or high calorific value. So this is how we assume that there is a total heat that is coming out from that particular fuel. So when a fuel containing hydrogen is burned, the hydrogen is converted into steam. So for example, if it contains hydrogen, then it is on conversion, it combines with oxygen and forms steam. Steam is nothing but water that is forming. So it is giving out steam. If the combustion products are cooled to room temperature, the steam gets condensed into water and latent heat is evolved. So when it is coming to room temperature, from high temperature to room temperature, it is converting to water and heat that is generated. So this heat is nothing but the heat that is coming out from the actual fuel, the complete heat, and is also called as the gross calorific value of that particular fuel. So the latent heat of condensation of steam is also included in the gross calorific value. So this heat, the latent heat of condensation from this product to this product, there is also heat that is coming out. So that is also included in the gross calorific value. That is why the gross calorific value is always higher. GCV is always higher than net calorific value. So a good fuel possesses higher calorific value. Definitely it should have higher calorific value, only then we can apply for different applications. So then coming to lower calorific value or the net calorific value. Net calorific value. So what is this lower or net calorific value? It is defined as the net heat produced when a unit unit quantity of fuel is completely burnt. So we are burning the fuel and there is also an escape of, for example, this is the coal. We are heating up, so there is a evolution of heat or the heat is liberated. So there is also heat that is escaping gases along with some heat. So the products of combustion are allowed to escape. We are allowing it to escape. So under normal conditions, what happens? Water vapors produced during combustion are not condensed. So in this case, we are not condensing to room temperature. We are not condensing to room temperature. We are allowing that gas or the excess of heat to escape. So, and escape as such along with hot gases. So, hence it will have lesser amount of heat available, which is also called as lower or net calorific value. So, the NCV is always decreases than GCV. It is always less than GCV. So if we want to really calculate gross calorific value or the net calorific value of a particular fuel, what do we have to understand? Like net calorific value, when there is an escape, it means the gross calorific value minus the latent heat of that water vapors we are allowing to escape. So we have to subtract them from the gross calorific value. So that actually gives the net calorific value of particular fuel. So it is also equal to GCV minus weight of hydrogen. So any fuel will be containing hydrogen. So hydrogen into 9. How did we get this 9? So for example, if there is a hydrogen in that particular fuel, when it is undergoing combustion, combines with oxygen and forms water. So it has two parts. So 2 parts of hydrogen and oxygen gives water. It has 2 parts. When we consider only one part is equal to 9 parts of water. 1 part is equal to 9 parts of water. We are doing it half. So in the half we get 1 part is equal to 9 parts of water that we are producing. So that is why we are taking 9 into latent heat of water vapor. So this is the heat that, for an example, for water vapors it is about 587 kilocalories per kg. So for any water vapor, that is the latent heat, there is a constant heat, latent heat value that we have 587 kilocalories per kg. So the hydrogen in the fuel reacts with oxygen to give water. So this is how we consider the water that is forming and also the parts of water that is forming from 1 part of hydrogen. So this gives a good formula to understand and give the net calorific value. So thus net calorific value is equal to gross calorific value minus 0.09 hydrogen into 587. So where H is percentage of hydrogen in the fuel. So anywhere when there is a fuel that has, it is given in percentage of carbon, percentage of sulfur, percentage of hydrogen and percentage of oxygen. Percentage of oxygen. So this is how it will be given. So here we are using percentage of hydrogen in the fuel. We are converting that into percentage. This 9 into percentage. So that we will be applying in the formula. So a person like scientist Dulong proposed a formula to calculate this calorific value from the chemical composition of fuel. So which is given as higher calorific value is equal to 1 by 100. 80 C is nothing but carbon plus 34,500 into hydrogen, oxygen by divided by 8 plus 2240 into sulfur. That will give in the form of kilocalories per kg. Kilocalories per kg. Why we have, this is the derived derivation that we obtained after experimentation of fuels. So this 100 is nothing but we are taking percentages. That is why we are dividing it by 100. Whereas C, H, O and S are the percentages of carbon, hydrogen, oxygen and sulfur in the fuel. So this formula, oxygen is assumed to be present in the form of water with hydrogen. So oxygen is always in the form of a moisture or water along with hydrogen. So low calorific value or the net calorific value is taken as HCV or the gross calorific value minus 9H by 100 into 587 is the latent heat of water vapor. So that will give in the form of kilocalories per kg. So this is again converted to percentage 0.09H into 587. So this will really give an understanding of both the higher calorific value and lower calorific value of particular fuel. So this is based on the fact that 1 part of hydrogen produces or by mass gives 9 parts of water that we have seen in the equation, and latent heat of steam is 587 kilocalorie per kg. So knocking, when we really use these heated or the calorific values when they are applicable, knocking is a type of disintegration that happens or the disproportionation going on. So in an internal combustion engine, IC engines we use in the automobiles. So a mixture of gasoline vapor and air is used as fuel. So gasoline vapor along with air, it means that combustion is going on. So combustion, internal combustion is happening. So gasoline along with air will act as a fuel. So after initiation of the combustion reaction by spark in the cylinder, the flame should spread rapidly and smoothly through the gaseous mixture. The ignition should happen smoothly and rapidly. So what it really happens if it doesn't? So thereby the expanding gas drives the piston down the cylinder. So this, when there is a proper ignition, the expanding gas drives the piston, or the piston will be going down the cylinder. So this is how the normal operation takes place. The ratio of gaseous volume in the cylinder at the end of suction stroke to the volume at the end of compression stroke of a piston is nothing but the compression ratio. So this is the ratio that we use in understanding the process where compression ratio. So it is nothing but the gaseous volume of the cylinder at the end of suction. Suction is like at its original position to the volume at the end of compression. When it is going, the piston is down to the cylinder. So that is nothing but the compression ratio. So the efficiency of IC engines increases with increasing the compression ratio. So the compression ratio has to be increased. Why? Because compression ratio should increase, should be high, should be high. When it is high, it means it is operating in a proper way. So which is dependent on the nature of constituents present in the gasoline used. So if there are any impurities, then the compression ratio will go down. So in certain circumstances, due to presence of some constituents in the gasoline used, the rate of oxidation becomes so great that the least portion of a fuel air mixture, it means the oxidation that is going on during this combustion reaction will be least. So the it's so great that the least portion of, very less portion of this fuel air mixture gets ignited instantaneously. So the instantaneous ignition goes low, so producing an explosive violence like this. So that is called as knocking. So this knocking is causing really loss of the efficiency of that particular engine. So the capability or the capacity of that particular engine goes down, indicating loss of efficiency. So what we really do when there is a knocking that is happening, if there is a knocking in the engines, we use anti-knocking agents. So the following substances are added to petrol in order to prevent knocking in the IC engines. For example, tetraethyl lead, like tetraethyl lead is put into petrol. Particles of lead and lead oxide are formed on combustion. So it will, on combustion, lead plus lead oxide are forming. So that will reduce knocking. This helps the petrol to burn more slowly and smoothly, preventing knocking of particular engines. So other examples are tetramethyl lead. So this is another example. So next is the BTBE, that is methyl tertiary butyl ether. So methyl tertiary butyl ether. So depending on the applications we can use, when compared to TEL, this is far better because the formation or lead compounds are hazardous in nature, so that also keeps polluting the atmosphere. Next is the octane number or the octane rating. So when we really understand what is this octane number or octane rating, we use these terms when there is knocking that is happening in the engines. So octane number is introduced to express the knocking characteristics of petrol. So we are using petrol for running the automobiles. If there is a knocking happening in the engine, then we say the octane number of that particular petrol. So it has been found that N-heptane knocks very badly, and hence its anti-knock value has been given as 0. So it is favoring, N-heptane is favoring knocking. So it has zero value for anti-knocking. So it is not supporting the anti-knocking property, so it is 0. On the other hand, isooctane gives very little knocking, and so its anti-knocking value is 100. So isooctane is little knocking. It means less knocking. So it is given as 100. It is giving very slight knocking, so it is given as 100. 100 anti-knocking. It means it is giving an understanding, an indication that the particular compound, when it is present, the knocking capacity will be increasing or decreasing. So this is how the octane number is used to designate or understand the property of that particular petrol in knocking. So whether it is favoring the knocking or disabling or disintegrating the knocking. So thus octane number is defined as a percentage of isooctane present in a mixture of isooctane and N-heptane. It means we generally favor, or we generally happens to go with the 100% anti-knocking because we doesn't want that knocking to happen. So that is the percentage of isooctane. The higher the percentage, the higher will be the anti-knocking property of that petrol. So the percentage of isooctane present in a mixture of isooctane and heptane. So isooctane is 100. So we have seen it has 100 anti-knocking property. So that is why it is given 100. So if we see, this is the carbon chain of isooctane. N-heptane is given as 0. N-heptane is given as 0. Then C10 number. C10 number is also used to give the properties of knocking or the understand knocking, but in the diesel. So this is used in the diesel engines, or when it is when the engines are running with the diesel. C10 number is used to understand the knocking property. So C10 has a very short ignition lag, and hence its C10 number is 100. Ignition lag. Lag means the ignition is faster. It is a shorter ignition lag. Short lag. It means it is fast in ignition. Very short lag is present, but still it is good with ignition. Therefore, it is given as 100. On the other hand, 2-methyl naphthalene has long ignition lag. So, it is not allowing the ignition to happen frequently or vigorously. So, it is given as 0. So, it is given as 0. The C10 number is given as 0. So, this is the formula of NC10. Hexadecane is also called as NC10 and it is given as 100, and this is the 2-methyl. So, 2-methyl naphthalene. So, 2-methyl naphthalene. So, this is given as 0. This is given as 0 C10 number. So, this is used in the expression of knocking characteristics of diesel. So, thus the C10 number is defined as the percentage of hexadecane, that is 100, present in the mixture of hexadecane and 2-methyl naphthalene. So, these are the compounds that are already present in diesel. So, the presence of this hexadecane will improve the anti-knocking properties. So, therefore, we are understanding in the form of like the percentage of hexadecane present in the mixture of hexadecane and 2-methyl naphthalene, which has the same ignition lag as the fuel under test. So, C10 number generally decreases. So, this C10 number decreases from N-alkanes. So, N-alkanes has the highest C10 numbers. Then cycloalkanes, alkenes, branched alkanes and aromatics. So, C10 number decreases when it is coming to aromatics. That is why this has 0. That is why the 2-methyl naphthalene has 0. So, the C10 number of diesel oil can be increased by adding additives. So, these additives is nothing but dopes. We want the C10 number to increase so that the anti-knocking property will increase. So, dopes are nothing but doping. We are doping. So, ethyl nitrate or isoamyl nitrate. So, these are the examples that are used as additives added to increase the C10 number. So, if you see the comparison, if the C10 number is used in the diesel and octane number or the octane rating is used in the gasoline or petrol. So, when there is a 20 C10 number, higher the C10 number, the fast will be the burning. The fast will be the burning. So, lower octane number. So, lower octane number, fast burning. Fast burning. So slow burning will happen when it is high octane number. So octane number is a measure of performance of the fuel. So the performance of the fuel is defined by its octane number, and C10 number is a measure of delay of ignition. So it will just give an understanding of delay in the ignition of that particular fuel. So it is important for predicting the knocking of an engine. So these two terms will help in understanding the knocking of that particular engine, and it is also important to predict the ignition of that particular engine with the C10 number. And octane number is used for the gasoline or petrol, and C10 number is used for this diesel. So octane rating is done considering the octane number of isooctane as 100. So octane rating is done with the isooctane, which is considered to be 100, and C10 rating is done considering the ignition of C10. So considering the ignition, it will just give an understand. C10 is ignition. C10 gives ignition property of that particular fuel. Octane gives performance. So the knocking should be lower. So this is how the octane and C10 numbers helps us in understanding the properties of that particular fuels, most widely used in the liquid fuels like petrol and diesel. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.